This video is sponsored by Brilliant. Mathematics has always been very useful, introducing complex concepts into a series of simpler logics. In the previous video, we explored how chaos can arise in something as seemingly straightforward as a spring system, using phase-space diagram for visualization. With just a slight tweak to the system's conditions, we witness the emergence of chaos, even in the springs. For instance, this closed cyclic curve of phase-space diagram shows that the energy is always conserved in the system. And the radius of this circle represents the magnitude of the total mechanical energy, with larger circles indicate that the system has higher energy levels than the smaller ones. But that's just a glimpse of what lies ahead. This curve represents the motion of a single particle constrained to only one dimension. In reality, we deal with millions of interacting particles. Instead of calculating the motion of every individual particle, physicists focus on the collective behavior of the system, calculating its total energy, entropy, or even momentum. Here's where the concept of an n-dimensional sphere representing the phase space becomes invaluable. Understanding its surface area and volume provides powerful insights into the behavior of complex systems. Let me be honest here. I really don't have a way to visualize the sphere in higher dimensions. Our perception is limited to the 3 dimensions as we experience in the real world, and this constraint limits our visualization power. So instead of struggling to picture the higher dimensional shapes, let's take a different approach. What I'm gonna propose is a blend of a geometrical and analytical approach, a method to intuitively and mathematically explore the volume of an n-dimensional sphere. And to build this intuition, we'll rely on the idea of projections, a shadow perhaps. Like the shadow of a high dimensional shape cast onto a lower dimensional plane. And thinking in terms of these projections offers a tangible way to grasp the mysteries of higher dimensions. Imagine a 3D sphere existing in our 3-dimensional world. To describe this sphere mathematically, we rely on 3 coordinates in a Cartesian system, x, y, and z. The defining feature of a sphere is its symmetry. No matter which direction you measure from the center, the distance to the surface remains constant, and this distance is a radius. The shadow it casts onto the 2D plane will be a circle of same radius r, and depending on the radius of the sphere, the size of this shadow changes accordingly. Now, for simplicity, let's take the radius r equals 1. Any random point on the surface of the sphere will always satisfy this equation. No matter the specific values of the coordinates, the sum of their squares will always equal to 1. Now, if I fix one of the values of the coordinates, say z equals 0, the sphere gets effectively sliced at xy plane. And as you can observe, the equation would become x squared plus y squared equals 1. And this equation describes a circle. Now, this dot will revolve along the circumference of the red circle. Depending on the value of z, the radius of this circle changes. As z moves closer to the poles, the radius of the circle decreases, and eventually collapsing to a point at the poles. And this radius and the radius of this red circle is maximum at the equator. For various values of z, we get multiple slices of circles with varying radii. These slices illustrate that a sphere can be thought of as being composed of concentric circular layers stacked on top of each other along the z-axis. In the same way, we can envision a 3D sphere as a single slice or a layer of a 4D sphere. Just as the 3D sphere is built from the stacked circles, the 4D sphere or hypersphere is constructed from the stacked 3D spheres, each corresponding to a specific value of the 4th coordinate. In a sense, 3D spheres act as the building blocks or layers that form the structure of a 4D sphere, offering a tangible way to imagine its higher dimension geometry. Now, besides the geometric intuition behind the slicing of an n-dimensional sphere, we also need the help of factorials. Factorial of any number n is defined as n factorial equals to n minus 1, n minus 2, to 1. For instance, the 5 factorial is equal to the multiplication of 5, 4, 3, 2, 1, and this equals to 120. Now, notice that 5 factorial is equals to 5 times the 4 factorial. And this relationship allows us to define the factorial function recursively. If f of n equals to n factorial, then I can also write f of n as n times f of n minus 1. However, the domain of this function is restricted to positive integers, and this makes fn discontinuous, as it is only defined as discrete points. But the question is, can we extend this definition to a more generalized function, where n can take any real or even complex value? For someone unfamiliar with such a continuous function, this idea might seem a little mysterious. But to find a formula for f of n that works for all real or complex n is a fascinating challenge. Let's revisit the factorial sequence to investigate further. Interestingly, factorials naturally appear when we differentiate the functions which has the form of x to the power n. For instance, if f of x equals x to the power 5, then differentiating this function 5 times with respect to x yields the value of 5 factorial. In general, I can get n factorial when the function x to the power n is differentiated with respect to x n times. This relationship is only valid when n is a positive integer, isn't it? So, I think we have to consider a different function. Maybe f of x equals 1 by x. Now, if we differentiate this function repeatedly, an intriguing pattern emerges. After n differentiations, the numerator of the result takes the form of n factorial, with the alternating signs depending on the value of n. And this suggests another connection between differentiation and factorials. And this relationship becomes even more elegant when we use the integral form. Consider this integral, which also gives the function 1 by x. If I differentiate both sides with respect to x, the equation becomes quite interesting. Notice how the negative factor cancels out from both sides? Now, differentiating the function, the f of x or this integral, n times would yield a value which is proportional to n factorial. Now, evaluating this equation at x equals 1, we obtain an equivalent form of n factorial expressed in integral form. And this is famously known as the gamma function. The beauty of the gamma function is that it generalizes factorials to any real or complex value of n. Well, remember this integral form. We have to use this later. To gain a deeper understanding of math concepts, I personally use Brilliant.org as a learning resource. And I would like to thank Brilliant for sponsoring this video. Brilliant is an interactive learning platform that helps you get smarter every day by building practical skills in areas like physics, problem solving, math, data science, and AI programming. What makes Brilliant apart is its hands-on approach to learning. Instead of passively consuming content, you will dive into the real and interactive problems that guide you step by step and help you build your intuition. Their courses are designed to fit seamlessly into your life, whether you are a beginner looking to build your foundation or an enthusiast diving deeper into topics like factorials, calculus, or even machine learning. Brilliant simplifies even the most complex ideas with a bite-sized interactive lessons. Recently, Brilliant enhanced their courses to make learning even more engaging, breaking down each concept into manageable bite-sized pieces. What I feel about maths is that it's never about memorizing formulas or even tricks. It's about truly understanding the concepts in a way that's gonna stick with you. One of the things that I love most is how easy it is to incorporate Brilliant into my daily routine. Whether you are tackling a lesson on your commute, taking a quick break, or winding down before bed, you will find yourself getting smarter one day at a time. So, why not explore everything that Brilliant has to offer? And you can try it for free for a full 30 days by visiting brilliant.org/warnix. You can click the link in the description or simply scan this QR code to get started. And here's the best part. If you sign up today, you'll get 20% off Brilliant's annual premium subscription. Let's start with a simple circle of radius r. Its area is well known, pi r square. Now, to prove that, we can begin by dividing the circle into several concentric rings with a varying radius and a constant thickness dr. For better approximations in finding the area of the circle, the value of dr should be very small. Let's isolate one such ring of radius smaller and thickness dr. While dr is extremely small in reality, well, close to 0, but for visualization purposes, I am going to show it with finite thickness. What I am interested in is the area of this ring dA, and that would be the product of its circumference 2 pi r and its thickness dr. Well, the total area of the circle is a summation of the areas of all these rings. Mathematically, this means integrating 2 pi r dr from r equals 0 to capital R. But for now, let's just focus on this ring. Remember that this circle is just the 2D projection of the sphere in 3D. And in the same way, these concentric rings represent the 2D projections of the concentric spherical shells. Now, for a sphere of radius smaller, its volume element dV is analogous to dA. In the case of dV, the formula would be the product of the surface area of sphere and its thickness dr. Again, if you want to compute the volume of the sphere, we integrate dV from r equals 0 to capital R. Let's hang on to dA and dV for a moment. Now that we understand how to find the volume of sphere in 2D or 3D cases, let's introduce some notation to generalize this further, to generalize to n dimensions. In 2D, the area of a ring is dA, which I'll now call as dV2, where the subscript 2 represents the 2D space. Similarly, in 3D, the volume of the spherical shell is dV3, where 3 represents 3D space. Now, notice an interesting thing here. Geometrically, the form of pi represents the total angle sweep by the boundaries of the shape around its center. For the circle, which is also a 2D sphere, this 2pi represents the total angle sweep by the boundary of the circle around its center. And in case of a 3D sphere, the total angle is 4pi steradian, representing the complete solid angle around its center. Let's call these angles omega, and the subscript shows the dimensions in which it resides in. To extend these formulas to n dimensions, notice that the power of r is always 1 less than the dimension number, which seems obvious as the volume of n-dimensional sphere is proportional to the nth power of its radius. In general, for an n-dimensional sphere, all of the work will be in the search for this omega n, which represents the angular sweep of the boundary in an n-dimensional space. Once we find the omega, the net volume of the hypersphere will be the integration of dV, where r goes from 0 to capital R. Even with the help of this formula, we can find out the total surface area of an n-dimensional sphere. The concept of the volume of a hypersphere is beautifully linked to this Gaussian integral, a cornerstone of mathematics whose value is square root of pi. Grant Sanderson provides an elegant explanation of the solution to this integral and the origin of the pi factor. Analytically, the solution involves squaring the integral and then transforming it into the radial coordinates, which leads to a simplified form. And the value of this integral found to be pi. Notice how the first integral resembles the total angular sweep of a circle. So the first integral is basically the omega-2, and when we observe the second integral, it can be further transformed into a gamma function by making a substitution r squared equals to t. And this integration gives me the expression of omega-2. And in the same way, we can find the expression of omega-3. For this, we just have to evaluate the value of I to the power 3. This substitution redefines the integral in terms of a function that generalizes the factorial to continuous values. And this allows us to extend the concept of volume to an n-dimensional sphere. In general, the value of omega n can be extracted by evaluating the value of I to the power n. Now, from this omega n expression, I guess finding the volume of a hypersphere will be easier. And after rearranging some terms, I would get the expression of the volume and the surface area of a hypersphere.